In organic chemistry, we use two different definitions of acids and bases. We use the Lewis acid, the Lewis base, and we will use the Bronsted Lowry. We're going to start with the Lewis acid and base. A Lewis acid is an electron pair acceptor, and that means the Lewis base is an electron pair donor. So let's give an example. If we have something like boron trifluoride, and boron trifluoride exists kind of like this, it's one of those Lewis structures. Boron has 3 valence electrons and therefore will make 3 bonds, but it can also make 4 bonds because it is in row 2. So it can fill out that octet. And let's say I react it with this Lewis base, and the Lewis base I'm going to use is ammonia. Now we see this lone pair of electrons here, and that lone pair of electrons can be donated to boron in order to complete the octet. And when that happens, we form a new bond where that red or pink arrow is aiming or is pointing, and we can form this new compound. Now this boron trifluoride, because it is a Lewis acid, we call this an electrophile. Specifically, that boron is acting as the electrophile. That's where the new bond is going to be made. The ammonia here, we call that our nucleophile, specifically the lone pair on nitrogen. So that nitrogen is acting as a nucleophile because it wants to give its electrons to make that new bond. Lewis acids and bases, electrophiles and nucleophiles will be very, very important for our substitution reactions. So some examples of electrophiles, if we had something like this compound, 2-bromopropane, this carbon is the electrophile. Remember, we have those polar bonds. The electron density is being pulled out towards the bromine. That makes this carbon an electrophile. Some examples of nucleophiles, we could have the hydroxide ion. All of those lone pairs make a nucleophile. We have the methoxide ion, also a nucleophile. We could also have the amine or the amino ion. We could have neutral nucleophiles as well. So water, the oxygen has 2 lone pairs. So it has the possibility of acting as a nucleophile. A pi bond can also be a nucleophile. So a nucleophile is going to be either a pi bond or a lone pair of electrons on an atom. And we will talk about that nucleophile as the atom or as the molecule itself, not necessarily as the lone pair. We also talk about our Bronsted Lowry acids and bases. Now, Bronsted Lowry acids and bases are where we are transferring a proton. So it's a proton transfer reaction. A Bronsted Lowry acid is going to be one that donates a hydrogen ion in solution. And a Bronsted Lowry base, so this is going to be donate an H, this is going to be accept an H. So if I have, say, a solution of ammonia and water, the lone pair here is going to take this hydrogen. So because we have a hydrogen transfer, this is going to be called an acid-base reaction. And then what we form is NH4 and OH minus. When we talk about Lewis acids and bases, we're talking about nucleophiles and electrophiles. When we're talking about a Bronsted Lowry acid and base, that's what we're going to be calling acids and bases here in organic chemistry. Something that can donate a hydrogen will be an acid, and something that can accept a hydrogen will be a base. So we have to look at our organic compounds and see how acidic are our hydrogens. When we have something like methane, remember methane is a carbon with 4 hydrogens attached. You could look at that and think that one of those hydrogens could come off as an acidic hydrogen, and it cannot. Or at least not easily. The pKa for an alkane, the hydrogen of an alkane, is very high. So it's going to be greater than 45. It's very high. But if you have something like ammonia, like this, the pKa of ammonia is about 35. And then if you have something like water, water is another one that most students are familiar with. So the pKa of water is 15.7. Now, when we're talking about pKa, we're talking about the acidic strength. How acidic, how likely is this hydrogen to be removed? We're specifically talking about the removal of hydrogens when we're talking about acids in organic chemistry. The greater the pKa, the less likely it is for that hydrogen to be removed by a base. The lower the pKa, the more acidic, the more likely it is for that hydrogen to be removed. Now, these are called element effects. What I have done here is I have worked out, remember our periodic table, we have CNOF. And so the acidity increases as you move across a row. pKa of methane being 45, of ammonia being about 35, and of water being on the order of 16. As we look at more of the acidity of our organic groups, then we also need to take into account what are called inductive effects. So if we have a molecule, let's say we have ethanol. So ethanol is estimated to have a pKa on the order of, let's say, 16. As soon as we replace one of our atoms with a more electronegative atom, so let's say I have CF3CH2, then this pKa will decrease. And that is because of the inductive effect, the electronegativity effect of pulling the electrons towards the fluorine. As that inductive effect occurs, this bond weakens. A weaker bond is a more acidic bond. Therefore, this trifluorosubstituted ethanol will be more acidic than regular ethanol. We also have what are called resonance effects. Now, we briefly touched on resonance. Whenever you have a pi bond and a lone pair that can delocalize. So let's look at acetate here. Whenever these pi bonds can delocalize, we have resonance effects. Resonance increases stability. Therefore, this bond for acetic acid is going to be more acidic because the conjugate base is more stable. Resonance effects tend to be more powerful than inductive effects. We also have some hybridization things to take into account. So if we have, say, ethane, and we can compare that to ethene, and then compare that to ethyne, like this, these are sp3 hybridized carbons. These are sp2 hybridized carbons, and this is an sp hybridized carbon. Now, the less hybridized you are, so the more S character you have, the more acidic the hydrogen becomes. So an sp hybridized bond here will be more acidic than an sp2 will be more acidic than sp3. So we have 4 effects for acidity that we need to take into account: element effects, inductive effects, resonance effects, and hybridization. Your lower pKa values will be associated with stronger acids, and in an equilibrium situation, the equilibrium will always lie to the side of the weaker acid.